Hi folks, welcome back to part 3 of this lecture, which is the first of the stats lectures for the dyspepsia module. And we were talking just before the break about what stats are for, and I was talking about how stats are really useful for summarizing, describing data sets. So now I want to move on to the second reason stats are really useful, and that is because they can be used for testing ideas in an objective way. So where are we? We talked about summarizing and describing data using summary statistics like the mean, the standard deviation. That's helpful, especially when coupled with graphics, which can visualize what the data set looks like. Helpful in spotting patterns, in getting a feel for your data. But more often than not, we want to move beyond that into testing a specific idea that we have about the way that the drug that we're interested in works, that kind of thing. We normally have a hypothesis, we want to test that hypothesis, and to get an objective test of the hypothesis, we're going to use statistics. So this stuff is taught in a very wide range of academic courses, from medicine to geography to psychology, and I've seen a million different ways of teaching stats, and very often it involves a lot of this kind of thing that you can see on screen now, lots of jargon. Maybe some maths, but certainly some sort of quite sort of abstract, maybe quite boring stuff. So I'm going to try to lead us towards these concepts in a slightly more intuitive and maybe user-friendly way, I hope. So we're actually going to work to start with an example. We're going to look at why stats might be useful without any of the kind of jargon or the maths initially. And then in next week's lecture, we're going to look at more of the sort of hardcore detail behind the scenes. So this example is going to involve some smelly poo and some tree resin and some flowers, believe it or not. So in a normal year, this example is kind of a nice, fun way of illustrating how stats might work. But it takes on a little bit more significance than normal this year because of COVID, because this is an example about a pandemic. And the pandemic in question is not COVID, but the plague. So the plague ravaged Europe, well actually probably most of the world, at various times during the Middle Ages, particularly in the 14th century and the 17th century, when it wiped out huge numbers, millions of people across Europe, as many as a third of the population of the sort of known world in Europe in the 14th century, for example. So a massive scientific problem equivalent to the problem with COVID at the moment. And so, unsurprisingly, the sort of budding scientists of the time, the pharmacists of the time, were interested in finding treatments for plague and trying to help people survive or maybe not get the plague in the first place. But this is an immensely difficult problem, especially when you're working in the Middle Ages and you don't have access to any of the information that we do now about how a disease like the plague might be caused. So the typical thing that people tried was to treat patients who were showing these horrible welts of the disease, getting sick, try to treat them with something that might maybe lessen the symptoms or cure the disease. And one real remedy that was tried at the time was a poultice made from tree sap or resin, the roots of lily flowers, and human excrement, because obviously, if you're thinking from first principles and you're trying to cure a deadly disease, smearing somebody with poo is bound to work, maybe. So anyway, this is a real remedy that was tried at the time. And I want to put you in the sort of role of the government trying to review whether this is a useful treatment that should be rolled out in pharmacies across the medieval world. So let's start with some basic facts about plague. And I've made these up, but this is sort of to illustrate the point. But let's just assume that if you catch plague, you've got a 50% chance of death. I don't actually know what the chance was. If this was COVID, obviously the chance of death would be, luckily, rather lower, but still a problem. So let's imagine you've got a 50% chance of death, and what we want to know is whether this remedy that we're applying to patients as a poultice is any good, whether it helps them avoid that death that otherwise would happen 50% of the time. So because we're good scientists, we're going to do an experiment, and we're going to apply this poultice to half of the patients that we've got, and maybe keep a control group that are untreated, and then look at the patients who've been treated to see what happens to them. So that's what we're going to do. And we're going to look at the data. And the data come in a categorical form. Each patient either survives or dies. Now bear in mind that we're treating people who've got plague, So 50% of them are expected to die if you don't treat them. And that's a crucial fact here. So what we're going to do is we're going to generate data by looking at patient outcomes. We're going to treat patients one by one. We're going to see what the outcome is. And I want you to think about when you should stop the trial. So just like with COVID, you don't want to carry on doing your vaccine trial forever and ever. You want to, this is a deadly disease. Once we've got evidence one way or another about whether the treatment works, we want to move from the trial phase into, well, if it's working, into rolling it out in pharmacies. And if it doesn't work, then we want to ditch it and move on and use something else. So it's really important to stop the trial at the right point. Not too early when you haven't got enough evidence that it works or it doesn't work, but not too late that you've wasted lots of resources. So I want you to think, as I give you the data, which are going to be patient outcomes, at what point do you think the trial should be stopped because we have convincing evidence that either the treatment works or it doesn't work? And in this situation, we're going to, because we know nothing about this bizarre remedy, we're going to allow for both possibilities, that the treatment either makes you less likely to die from plague or more likely to die from plague, or it has no effect. Okay, so kind of all possibilities could be on the page, and we're going to look at patients who have a 50% chance of dying normally, and I want you to see the outcomes and decide, okay, after so many patients, we've now got enough evidence to say the poultice definitely reduces the chance of death, or increases the chance of death, or definitely has no effect. Okay, so here we go. So we apply the poultice to the first patient, and the answer is that patient died. Okay, so at this point, just make a note, or mental note if you like, if you think that that's enough evidence to stop the trial. We've got a 50% chance of death normally. We've looked at one patient, that patient has died. Have we got enough evidence to show that the poultice either doesn't work or is, maybe even causing patients to die? Well, let's carry on. So I'll tell you, the second patient also died. So we wonder, is that enough evidence? 2 patients in a row, 50% chance by, normally. So think about this maybe as a toss of a coin. 2 deaths in a row. Some of you might have decided to stop by now. Some of you may want more evidence. So let's get some more evidence. Aha, third patient died. We smeared them with excrement and tree resin, and they died. Remember, 50% chance of dying of the plague anyway, so 3 in a row. Have we got enough evidence? Those of you who are not convinced, I'm going to show you some more evidence. Next patient died. Is there enough evidence to stop the trial? Bear in mind, people's lives are at risk here, obviously in the trial, but more generally, there's a whole population of people dying, 50% of people dying of this disease. We've got a promising possible remedy. Have we got enough evidence? Are we convinced the poultice, well, it looks like it might not work. Are we convinced that it doesn't work and therefore we should stop the trial? Next patient died. Oh dear. So not looking great, but chance events, 50% chance of surviving, 50% chance of dying. Is this really evidence that the poultice doesn't work? Some of you may think so, some of you may not. So let's carry on. Next patient died. Oh dear. Okay, anybody unconvinced yet? Another patient died. And finally, we find actually in this case, all of the patients in our sample died. So at some point in that process, hopefully, you made a mental note. Yeah, right, I think there's enough evidence now that we should give Matt Hancock a call and say, stop smearing people with poo. It looks, on the face of it, from those data, that this poultice doesn't improve your chances of survival, and maybe it actually makes you more likely to die. I mean, with modern medical knowledge, I think if you were smearing somebody with excrement, you'd think it's not going to help and it might make things worse. What's going on here? Okay, you each have made a decision to stop the trial at a different point. But actually, when I do this in the lecture theatre and I get people to give me a show of hands when they feel like they should stop, I tend to get an unerringly similar answer from most of the people in the room. Most people will want to stop the trial after around about 5 deaths have happened in this particular situation. And so you might think, well, that's just kind of intuition, feels about right. 5 deaths when there's a 50% chance of dying normally. 5 in a row seems pretty bad, seems pretty unlikely that the poultice is doing any good. But we can actually do more than just sort of squint at it and think maybe that's intuition. We can think about this mathematically. What we can ask is, well, what is the probability of that many deaths happening by chance if the poultice has no beneficial effect. So if the poultice doesn't reduce your chance of death, then your chance of death would be the background probability of 50% or 0.5, ignoring for the time being that it could actually make things worse. If the poultice is having no effect, if the background probability of death is remaining the same in the trial, then we'd expect 50% of the people that we saw at the end of the trial to have survived and 50% to die. So the probability of seeing one patient in a row dying during this trial, if the poultice is having no effect, is 50%. But the probability of seeing two in a row, both of the patients in a trial that has two people dying, assuming the poultice has no effect, is 25%, because it's 0.5 times 0.5. And the probability of seeing three people die in a row out of a sample size of 3, if the probability of death is 0.5 for each individual, is 0.125, because it's 0.5 times 0.5 times 0.5. And this goes on. So if you have 8 people in a row dying when the probability of any individual dying is 0.5, then the probability of seeing 8 people in a row die is about 4 in 1,000, 0.004. Think about it another way. If you've got a coin and you toss it 8 times, the chance of you getting 8 heads in a row is about 4 in 1,000, unless the coin is biased in some way. So what you guys chose probably is to stop the trial when the probability of seeing what we had seen by chance, if nothing interesting was going on, if the poultice was having no effect, was somewhere between maybe about 3% and 6%, somewhere around about this place here. So the probability of 5 deaths in a row was 3%, probability of 4 deaths in a row about 6%. So it's at that point that you start to think that the data do not look like what's happening is just happening by chance. Instead, actually, it looks like something different is happening. And in our case, it was actually worse than 50% chance of survival. Everybody was dying. So by the time we got to 5 people dying in a row, what we're saying is the chances of that happening, if the poultice was not having any effect, are pretty small, 3%, so small that we're fairly confident that what's really going on is the poultice is having an effect. It's actually killing people. So we should stop the trial and abandon this as a possible treatment. So what you've done there is actually come up with the threshold p-value, and we'll talk more about p-values in later lectures, that we use in modern statistics, typically in a discipline like pharmacy. In general, scientists tend to agree that if you see something that has only maybe a 5% or less chance of happening by chance, then that probably means that something else is going on to explain why you've seen the event that you've seen. So in our case, the chances of seeing all those dead bodies, if the poultice really didn't matter, was so small that we conclude that the poultice did matter. That's essentially the essence of statistical testing, and doesn't matter how many fancy computers and silly test names you come up with, the process is always the same. What you're doing is you're calculating p, the probability of observing what you have observed by chance, if there is no effect, no difference, no trend, no interesting phenomenon going on. So let's put a little bit of jargon on this process. What we actually did here was we took a sample from a population. So the sample was a bunch of patients, hopefully chosen at random from the population of people who've got plague, and each of them we looked at what the outcome was when we gave them the treatment. So the sample is a subset of the population, and it should be representative in order for us to reach an objective conclusion. So by representative, what we mean is it should be, in this case, randomly selected from all of the people who are valid in the population. The valid population here is people who have plague. We want to know whether their probability of death is affected by the poultice. So we choose some of them at random and we apply the treatment, and then we collect some data. So that process lies at the heart of pretty much all statistical testing of the sorts of things that you're going to see in future years of your degree, and indeed it lies behind it's basically the process that's required when you're assessing the evidence for the efficacy of a new drug or a new treatment. And it's exactly what's going on or has gone on with the vaccines that are being developed for COVID. This is exactly the kind of data that they've looked at. They have literally looked at whether patients got COVID or not, so kind of binary thing, or whether they died or not, perhaps, whether they got bad symptoms, whether they were hospitalized. They've looked at those outcomes in a sample, because you can't look at everybody in the global population, a randomly or representatively chosen sample from the population. And then they've asked themselves, well, what's the probability of seeing what we've seen if the vaccine really doesn't have any effect? Okay, so we're going to return to that idea continually, actually, over the next couple of lectures. But it's a really crucial central concept. And as you can see, you don't need any maths or much jargon to understand it, hopefully. So just some take-home messages from today's lecture. I started off, if you remember, by talking about the different kinds of data that we encounter in the natural world. And we can kind of usefully categorize those data into different types. And it's useful for you to do that so you can recognize the sort of statistical problem that you have when you're collecting data. We can use stats to describe those data, slightly different ways for different types of data, but they are really useful for descriptive processes, and in which case we call them summary statistics. Graphs and tables, figures are really useful also for describing, visualizing data. And then we looked at statistics in the evaluation of an idea. Okay, so using data to evaluate how plausible your data set is given a particular idea. That's the sort of thought process we go through. So we collected some data and we said, well, how likely is that if a particular idea is true? In our case, if the treatment was not having any effect, what would the data look like? If the probability of the data looking like they do is really, really small, expressed as a probability, then we conclude that there's something funny going on. Okay, so we're going to return to that idea, like I say, lots in future lectures. So just to sort of distill that down to one key message from today's lecture, what I want you to be able to walk away from this with is an understanding of what stats are for. So if you didn't get anything else from the lecture, really try to focus on remembering what the point of using stats is in pharmacy or any other scientific discipline. Okay, thanks for that, for listening and concentrating. Next week, we're going to have a different kind of take on the same problem that I've just presented to you, this idea of using stats for testing. And what we're going to do is specifically look at particular kinds of tests that target differences. So where we're looking for a difference, just as we were actually in our patients, a difference in outcome between those receiving a treatment and those not, perhaps. And I'm an ecologist, so I always like to illustrate these things with pictures. So I'll explain what these snakes are about in the next lecture. Okay, so that's me done.